This is the third lecture for Text Unit 3. Before we begin with the subject of today's lecture, let's try a quick review question. How many grams of carbon and 100 grams of carbon disulfide? Attempt this problem on your own. Pause the presentation of the attemptant, and then move on to the solution. You need the molar mass of carbon disulfide, which is 76.145 grams. Each carbon disulfide has 1 mole of carbon, so you need the mass of 1 mole of carbon, which is 12.011 grams. Divide the mass of the carbons by the mass of the carbon disulfide. Multiply it by 100%. Note the grams have canceled. The answer is 15.774%. To answer the question, we take this percentage in decimal form, 0.15774, multiply it by the mass of the sample, 100 grams of carbon disulfide, and the answer is 15.77, and this is grams of carbon and 100 grams of carbon disulfide. The new material in this lecture is concerned with stoichiometry calculations with chemical reactions and equations. As we saw in Unit 2, chemical change produces new substances from old. We can express this with a chemical equation which shows the old substances, reactants, and the new substance, product. So for example, we know that hydrogen is made, that water, is made of hydrogen and oxygen. Here we have an equation where hydrogen and oxygen make water. Now when chemical change was defined, we actually just defined it as a change that produces new substances. However, atoms are not created or destroyed in a chemical change, so if a new substance is getting made, old substances, the reactants, must be getting used up. The number of atoms for the process, atoms of each element, is the same before and after the change. For that reason, we balance chemical equations to reflect that. For example, here is a balanced chemical equation for the reaction of hydrogen and oxygen to make water. 2 H2 react with 1 O2 to produce 2 H2O molecules. The numbers in front of the species are coefficients, and notice now there are 4 hydrogens before, 4 hydrogens after, 2 oxygens before, 2 oxygens after. Note also that we had to write H2 and O2 as molecules, as discussed in Unit 2. Coefficients must be the set of smallest whole numbers that balances the chemical equation. If you'll look in your text, there are rules of thumb for balancing that I will not fully reiterate here. I will emphasize the importance of checking your work when you're done. In other words, when you think you have a balanced equation, go back and make sure that the same number of atoms of each element is on the left as on the right. So again, up here, 4 hydrogens on the left, 4 on the right, 2 oxygens on the left, 2 on the right. Using the textbook freely and looking at examples therein and the rules of thumb, go ahead and attempt to balance the following equations. I've provided 4 examples. Here are the solutions. First, note that for this reaction there are no changes. The equation is balanced as it's written. That may happen sometimes. second coefficient is, the second reaction is balanced by putting a 2 here, a 2 here, and a 2 here. Could have been balanced more simply if we could have put a 1/2 here, but coefficients cannot be fractions. Balance this equation, we end up with putting a 6 here and a 6 here to balance carbons and hydrogens. Remember, oxygen is a free element and should be balanced last. It turns out the final step in balancing is to put a 6 here for the oxygen. This reaction is similar to the one above, except that it makes carbon monoxide, not carbon dioxide, and here is the balanced equation for the final reaction. All right, what can you do with a balanced equation, or what is the point of balancing? All right. Here I have one of the balanced equations from the last example. Each coefficient can be read as moles, and notice that if there is no number, that implies a 1 here. So every 2 moles of sodium reacts to produce a mole of hydrogen, or 2 moles of sodium, when we're talking about this reaction, is equivalent or related to 1 mole of hydrogen. Similarly, 2 moles of sodium can be related to 2 moles of water, and etc. for every pair of species in that balanced equation. All right. So suppose you have a question like this. How many grams of H2 are produced or made when 10 grams of sodium reacts with excess water? Right, I will use the word, what the word excess means in this case is just that there is more than enough water around to react with the 10 grams of sodium. All right. This is the first of many problems you will work using the mole highway in this course and in other chemistry courses. Stoichiometry problems like this are basically unit conversion problems. First thing to do, what you do with all unit conversion problem is write down what you know about, convert that to moles. Then you'll convert moles of this to moles of what you want to know about using the balanced chemical equation. Then, if necessary, you convert moles to whatever is needed for the answer. Right, to make these 3 steps more clear, let's look at our example problem. All right. The thing we know about is that we have 10 grams of sodium, so that's our start. Okay, step 1 means use a unit conversion factor to convert this to moles. Okay, so I would take the 10 grams of sodium and multiply it by 1 mole over 22.9898 grams. Grams to moles with this unit conversion factor. You've executed this step many times before. The next step is to multiply the solution, which I don't even write down. I just write down the next factor in this case. And the next factor converts moles of sodium to moles of H2. Moles of H2 appear in the numerator, moles of sodium in the denominator. Moles of sodium will cancel and leave moles of hydrogen. So, this times this gives us moles of sodium. This times this times this cancels moles of sodium and gives us moles of hydrogen. I notice that the 1s and the 2 here are coefficients provided by the balanced chemical equation. In the final step, moles of hydrogen are converted to grams of hydrogen using the molar mass. So this is a conversion factor to convert from moles of hydrogen to grams of hydrogen. And the solution to three significant figures is 0.438 grams of hydrogen. Let's review the steps again. Start with what we know, multiply by a factor converting it to moles. Second step, convert from moles of sodium to the thing we want to know about, which is moles of hydrogen. Here we have a unit conversion factor, 1 mole of hydrogen in the numerator, 2 moles of sodium in the denominator. The 1 and the 2 come from the balanced chemical equation. Moles of hydrogen is then converted to grams in the last step, and we have our solution. Step 1, step 2, step 3. Grams cancel in step 1. Moles of sodium cancel in step 2. Moles of hydrogen cancel in step 3. And we're left with grams of hydrogen. Alright, I said there was excess water. How much of that reacts, or how many grams of water react? Balanced chemical equation says 2 moles of this is related to 2 moles of water. We're assuming the same reaction, that we start with 10 grams of sodium. So in this same process, how many grams of water react? Start with what we know about, multiply by a factor that converts it to moles, multiply by a factor that converts moles of sodium to moles of H2O. The 2's in this factor are from the balanced chemical equation. Then a multiplication to convert from moles of water to grams. And the solution is 7.84 grams of H2O. Okay, let's move on. Look at one last one. This takes another equation that we balanced earlier. And let's ask the question, if 15 grams of carbon dioxide are produced, how many moles in grams of water are produced? Here we see that it's possible to use stoichiometry to relate one product to another product. So here's the question, again, reiterated again. So here's the solution to the question about the moles. Begin with what we know, 15 grams of carbon dioxide. Convert to moles of carbon dioxide. Then we have a factor to convert from moles to carbon dioxide to moles of water, using the balanced chemical equation. And there we stop because the question is about moles. And this times this times this gives us moles of water. The answer is 0.341 moles of water. Right, if you haven't attempted to find the solution in grams, go ahead now and then look at that, and then move on in the presentation to look at the solution to that. Grams can be found two ways. Since we've just found moles of water, we can multiply that by the molar mass of water to convert to grams. Or, if we want to start from the very beginning and use the mole highway, first step is to convert grams of carbon dioxide to moles. There's step 1. Step 2 is convert from moles of carbon dioxide to moles of water. That's accomplished by multiplying by this factor. And then a final factor to convert from moles of water to grams of water. And the solution is 6.14 grams of water. So you could have start from the very beginning, Step 1, Step 2, and Step 3 obtain the answer, or since you already knew moles of water, you could simply convert that to grams, and you obtain the same answer. And this concludes the third lecture for Text Unit 3.